This is 150 North Riverside, a building here in Chicago that looks a little strange. At its base, it's almost like the tower's been eaten away, leaving only its core behind. You might think that this would make the entire building structurally unstable, and you'd be right if this feature wasn't compensated for in the design and construction process. You might also wonder why anyone would go to such trouble to cut out that part of the building. What benefit does it serve? And then I guess I have the follow-up question, how? How can a building so massive balance on this tiny little line? The building was designed by Goettsch Partners, an architectural practice with a particularly spectacular office space in downtown Chicago. It's filled with models of buildings proposed and built all over the world. And it turns out that this unusual solution came from solving some relatively straightforward, pragmatic problems that were inherent with the site that the building sits on.
I guess you have to have an interesting problem to have an interesting solution.
But that doesn't mean that the solution came easy. The site is located on the southeast side of the confluence of the three branches of the Chicago River: the stem, the North Branch, and the South Branch. This natural configuration, in the shape of an upside-down peace sign, can be found all over Chicago, and it serves as its municipal device. That's also the shape that this tower makes here at the ground, a giant Y shape that pierces the earth below, then flares at the top to spring into 50 floors of office space. On ground level, we can experience the underside of the Y along the Riverwalk and in the lobby of the tower.
When we designed it and the way this solution came about, there's a certain lightness to it from the side, and airiness, how it kind of almost distances itself from the ground.
For over 100 years, this site was just a functional rail yard. It was one of the few rail yards left from the days when they lined the river. Back in those days when the river was used mostly for transporting goods and services, connecting water transport of the Great Lakes with the rail transport throughout the Midwest. These tracks still exist. They're just underneath this park, and today they're used by Amtrak travelers arriving to or leaving Chicago. These tracks were actually one of the primary factors for why the tower only touches down the way that it does.
You know, the site it's probably, before it was developed, probably the largest open space in the city.
You see, all the tracks had to stay exactly where they are, and they had to stay fully operational during the construction of any building above. So the overall footprint of the building was strictly determined by a series of requirements on each side of the site that, when fully mapped out, gives you the only place where the building could go. There's the river and a city-mandated 30-foot or 9-meter wide continuous riverwalk to the east. Then on the west, you have the Amtrak tracks, and the leftover buildable area is only 35 feet. This is why the site sat relatively vacant for all those years. It was vastly underutilized. But this is the perfect place for a building otherwise.
We have all these different modes of transportation that are not even visible in some degree, but we just had the L passing by. You have the boats on the river, you have pedestrians moving, you have cars, and then you have trains, subterranean and elevated. So, I mean, that really makes the site incredibly interesting. It was so isolated to some degree. It has so many different levels. It's very interesting, and we try to translate that into the architecture to some degree.
But it seemed almost impossible to build anything substantial within such a limited space.
What's actually happening is the core has all of the vertical forces, and then the perimeter columns are being transferred in, and they're canceling each other out.
If we look above the 8th floor, it's a regular building. It's got perimeter columns, it's got a core. All the forces are very well organized. Because of what we're ultimately doing with the core supported building, we had to keep a very symmetrical building and keep the forces organized. So we get to the 8th floor, we bundle all the forces together through this triangular truss, and we load them down into the core. And then they've got to go all the way into the earth, into the caissons.
There's almost a separation between the ground plane and what's happening above. And the building very lightly touches the ground. Only 25% of the site are occupied actually by enclosed space. Everything else is open to the public. But I think here you get a good glimpse of the experience of the overhang, which isn't oppressive at all. I think it's very open and like how the light channels in.
The tight physical constraints meant continuous challenges throughout the construction process. For instance, there's no place to put a construction crane that could anchor into the solid land, so a barge was planted here for a couple of years. It became such a staple around here that it's been immortalized on Google Earth.
A crane or a truck to park on the street, you need all these permissions from the city and permits from the city to put an 80-foot square barge in the middle of a river. I think it seems like, they make it sound like it was just a phone call to the Coast Guard and they're all set.
The crane was instrumental in hoisting some pretty spectacular elements into place. That includes the arms of the Y-shape, which were made entirely out of steel. These elements precariously spring out of the concrete core and transfer all of the loads of the outside floors above. The forces are so great, these steel members are the largest I-beams ever made. They weigh 1,000 pounds per foot of length and had to be specially designed and made for this project.
We would see people, especially once the steel started going up, take your lunch breaks out on the Randolph Street Bridge and just watch this thing because it was on full display for everybody.
This Y-shape then produces some peculiar conditions inside of the building structurally. For instance, the outside of the tower wants to flare outward at the bottom, pivoting on the steel members. So the entire first office level is actually in tension, being pulled apart, which of course was designed into the building and its construction. The tower deploys a technique called a tuned mass damper, which fundamentally is just a giant concrete water tank at the top of the building. It sounds counterintuitive that adding water weight to the top of a building would actually make it more structurally stable. But gravity is an easy thing to overcome with a scheme like this. The problem is wind. The tower sits on such a small footprint that it needs to resist getting pushed over, and that's where the tuned mass damper comes in. I created a bit of a demonstration here with these MOLA structural kits. The water has a large moment of inertia. It's heavy, and it doesn't move very fast. At the same time, it sloshes around. Its weight can be distributed differently depending on where the water sloshes. So what happens is, if the building is pushed by the wind, it bends a little bit, but the water moves slower than the building does, so its weight is back over the original center of gravity. This basically pulls the building back into shape before it's allowed to bend too far. It also sloshes at a different frequency than the building moves, creating a dampening effect overall.
So it's a reverse pendulum effect. So as the building moves this way, the force moves that way. So you get these counteracting forces. And we just want that water to hit the opposite wall with enough force to push the building back so we stay mostly plumb.
You can't go into that water tank at the top, but you can go into the lobby, which does its part to tell the story of the building as well.
I think you can feel the notion that it's almost like the core is holding up this element that's hovering above. So if you have this darker stone on the outside that wraps around, but then when you slice it, it becomes this light stone. So it's almost like we're taking slices out of the core and revealing you have the apple peel on the outside and then you reveal with the light stone. Even so, we had to create some enclosure. We wanted to make it as transparent and permeable and connective between inside and outside, is really creating this transparency to create a seamless transition between the inside and outside.
We enclosed it with a curtain of glass hung from the tip of the truss and draping down. So it just kind of hangs from the edge of the building. And as the building kind of tilts and turns, this glass will kind of rise and fall out of a pocket.
Heading up into the building,
So I think that's our elevator.
there are some unique spaces that come from this structure and the way that it projects out into the city.
Yeah, I think it's a very nice to have the fitness center in this part of the building with the incline and people doing their workouts looking out onto the river in a very special way is pretty cool.
Then on the 18th floor, the other side of the river becomes an incredible immersive panorama.
I think this is actually a nice level of, like, we are still in the city. We're not, some certain floors at the upper levels, you're almost out of the cityscape. So here it's like you still feel like you're in the heart of the city and all the elements we already talked about.
This design reminds me of some other buildings with bases that are smaller than their towers. Some that come to mind are the Rainier Tower in Seattle and the Citicorp Tower in New York. The Rainier Tower was designed by Minoru Yamasaki and looks like a miniature World Trade Center with bites taken out of the bottom. Locals call it the Beaver Building. This solution was to maintain as much free space at the base as possible. But the curved shape does channel winds in powerful and unpleasant ways. The overall effect is particularly unsettling as Seattle gets a lot of earthquakes. But the building has gone through rigorous testing and was actually one of the safest buildings in the entire city. But that is not the case of the Citicorp Tower when it was built, which lands on a series of columns that are offset from the corners. Visually, the base looks smaller when viewed at an angle. This building famously had a flaw in its steel details that slipped through the cracks during the design phase. This critical mistake left the building in danger of collapse after construction. Welding crews went through the building at night, reinforcing all of the joints to make it safe. Luckily, they were able to get it done in time before catastrophe struck. 150 North Riverside is a bold structural solution to a constrained set of site conditions. These kinds of feats only become viable where real estate prices justify their cost. That's the kind of equation that gives us hovering buildings in all sorts of urban environments. Here in Chicago, it's not quite as common as, say, in New York, where air rights transfers and incredibly high square foot values will yield very complex concoctions. But this version is an interesting and relatively subtle condition that you may or may not notice, depending on how hard you look. But I think that's the real sweet spot here. A lot of engineering went into creating this pleasant composition of space, architecture, and infrastructure without the spectacle getting in the way of enjoying it.